Swayam Prabha. Digital India. Educated India.
Okay, so let's start with our discussion related to lecture number 7, and we continue with our discussions related to different techniques for circuit analysis. And today we look at three techniques. They are Thevenin's and Norton theorems for developing equivalent circuits, and related to that is source transformation. Okay. All right, so we discussed in the last lecture that mesh and nodal analysis are general purpose techniques, but they're often take lot more time, they're error prone, and they yield expressions which are do not give us much insight into the operation of the circuits, and thereby they are not as useful if one is thinking of modifying a circuit or designing them. And we said that we want techniques that give us that are simpler to use, and they give us structured expressions which reveal the role of different components. And further, if they have the property of being less error prone, and if they require less effort, then those techniques would be very useful for us. So in that context, we had seen certain techniques in the last lecture, like use of superposition theorem and a methodology based on reusing results that were derived earlier, and like series and parallel resistance, voltage and current division. So before we go into these techniques, let's look at a problem which many times we encounter, which is a problem of power transfer. So the question here is, suppose we have a load resistor RL and we have a voltage source Vs and this resistor R. So let's say for a moment that Vs is fixed and R is fixed. And what we are looking for is what value of load resistor should we connect such that the power transfer or the power dissipated in load resistor is maximum. All right. So the problem is determining an appropriate value of RL given Vs and given R. All right, so we know that power dissipated in PL will be the current I square times RL. And the reason why there is an optimum value of RL is, note that if you can maximize the power dissipated in PL by, let's say, you may try to increase RL. So this term increases, but then as you increase RL, the current flowing in the circuit decreases. And therefore, while this term increases, this term decreases here. And because of this conflict here, there is a optimum value of RL at which PL is maximized. So let's find that out. So the current here is I, and I will be equal to simple single loop circuit. So Vs by R plus RL here. Power is I squared times RL. So we can substitute this expression here. And we see PL depends on RL. RL is in the numerator, as well as RL is in the denominator, and that's where if you try to increase RL, PL tends to increase because of this term, but it tends to decrease because of this term. So to find out the optimum value, we take derivative of PL with respect to RL equated to 0, and if we do that, what we get is that the condition under which this is true is RL equal to R. So and we can then substitute RL equal to R in this particular expression here and obtain the maximum power that can be extracted by connecting a resistor whose value is basically equal to R. So this maximum power transfer is saying that if you want maximum power to be transferred from the source to the load resistor, then you should choose the load resistor which is equal to the value of this resistor R here. All right, so it's a useful result. And as an example, let's say if I have 5 volt and 1 kilo ohm, and suppose I connect RL equal to 1K, then that's an optimum value we just learned. We can calculate power is 6.25 milliwatt. If I connect something larger than 1K, let's say 10K, we can calculate again power is 2 milliwatt. It's less. Similarly, if we connect something which is smaller, let's say 0.2K or 200 ohms, power is again smaller, 3.47 milliwatt here. So for both RL above 1K and below 1K, power is going to be smaller. At this value of RL, power is maximized. Okay, so it's a useful result. So maximum power is delivered to the load when RL equal to R. Now, after deriving this useful result, we would like to reuse it in more complicated circuits. So remember, one of our approaches was that we don't want to do analysis from scratch. That we would like to do analysis of certain circuits and certain results, and we would like to remember them and deploy them in order to simplify circuit analysis. Okay, so this is a useful result and we would like to employ it elsewhere also. So we had seen this Wheatstone bridge and we had derived this expression for the voltage across this resistor R0. Let's say this is the load resistor in terms of VSS and the rest of it. Now suppose we ask the question, what value of R0 should we put here such that the power dissipated in R0 is maximum? Let's say R1, R3, R2, R4, VSS all are fixed, and we have a choice over selection of R0, and we are asking what value of R0 should we connect here so that the power dissipated in R0 is maximum. Now obviously this question is related to what we just did, but then this circuit is far more complicated than the previous circuit here, which consisted of only one source and one resistor here. So it is more complicated. Of course we can, power dissipated in R0 would be V0 square over R0, and we can take this equation and manipulate it and by a similar procedure obtain the answer. But what we are looking for is, can we use the result that we just derived in a more direct manner? All right, so let's see whether that's possible. Now in the previous lecture I'd also said, and we will see how to do this in this particular discussion here, that if we take this particular circuit, we can write the voltage developed across R0 in this particular manner here. V0 is VSS, R2 by R1 plus R2 minus R here plus this term here. And how we can write it, we'll see as we progress in this particular lecture here. But let's for a moment suppose that we can write it like this here. And let's suppose this is correct. Now if you look at this equation, I can write this equation as V0 is VTH into R0 by R0 plus RTH. This part of the expression is nothing but a voltage, and this is what we are calling is VTH here. And when we come to the second term, this term in the bracket here is what we are calling as RTH, R1 parallel R2 plus R3 parallel R4. So what we are saying is the voltage across R0 can be expressed as V0 equal to VTH multiplied by R0 divided by R0 plus RTH. Now when we have this expression, we can display this equation in the form of a circuit, right? So let's say this is VTH, this is RTH, and this is V0. So you can easily see that V0 will be equal to VTH multiplied by R0 by, it's a voltage divider circuit, R0 by R0 plus RTH here. Normally we go from circuit to equations, but here we are saying you can do the opposite also. We have an equation and we have written it out in a circuit form. So this is interesting. What we are saying is that if you focus your attention on R0, right? If you this is R0 here. If you remove R0, let's say for a moment, the rest of the circuit, see R0 is over here also. So we are saying the rest of the circuit, R1, R2, R3, R4, VSS, can be approximated by, not approximated by, but can be transformed into a voltage source VTH and RTH here. So this whole circuit that you see here with R0 removed, and between these two terminals, when we look at these two terminals here, right, this whole circuit can be transformed into a voltage source and a resistor here. That's what this particular expression is telling us. If this expression is correct, then it says that this expression can be expressed in a circuit of this form, which implies that this entire circuit that you see here minus R0, okay, minus R0 here, this entire circuit here can be represented as a voltage source and a resistor. And if you can do that, then our original problem of what R0 should I connect here in order to get maximum power dissipation, the answer is obvious. Choose R0 equal to RTH. So it becomes very simple. The result that we derived earlier can be applied to this particular circuit. R0 is RTH. And how were we able to apply? because the complicated circuit that you see here, we could transform it into a voltage source and a resistor here. So this is what we mean by, and what we'll see is called the Thevenin's equivalent of this particular circuit. So let's see how we can do that. So the basic idea in Thevenin's equivalent circuit is the following. Let's say we have a circuit, and let's divide the circuit into two parts. There's a part here and there's a part here. And we would like to develop an equivalent circuit of this particular part for whatever reason, for simplification or there may be other reasons for doing it. So let's say you want to develop a Thevenin's equivalent for this particular part of the circuit here. What do we mean by Thevenin's equivalent? We are saying that this part of the circuit can be represented by a voltage source and a resistor source. Under what condition? Well, this circuit has to be linear. It has to be a linear circuit consisting of resistances. It can consist of any number of independent or dependent sources, but it has to be a linear circuit. The other part can be anything. It can be non-linear, it can be a resistor, it can be a diode, transistor, anything it can be. So it's any circuit here. We are not bothered about this part. What we are saying is this part of the circuit can be transformed into a part like here with a voltage source and a resistor. So that's very interesting. This part can be quite complicated with many resistors, many sources, and can be there here. It can have, let's say, 5 independent sources. It can have 4 dependent sources. It can have 10 resistors. But all of that can be replaced by a voltage source and a resistor. In what sense? That if you look at the terminal characteristics here, terminally, this circuit is same as this circuit here. We talked about in what sense are we building equivalent circuits. We said in terms of the terminal current voltage characteristics here. So if you took this part here and you replace it by VTH and RTH, well, no change will occur in the overall circuit. For example, if let's say a current was flowing 1 milliampere somewhere here in this circuit, if you took this out and you replace it by a VTH and an RTH, appropriate value of VTH and RTH, and connected it like this, the same current would continue to flow here. Right? So in that sense, from the terminal current voltage characteristics point of view, this part behaves in the same way as VTH and RTH here. Okay? So this is what we meant, that if you're interested in R0, then what happens is between these two terminals, the terminals across R0, between these two terminals here, the rest of the circuit can be replaced by VTH and RTH because the rest of the circuit is linear. It just consists of resistors and a voltage source. So that's what Thevenin's equivalent circuit is telling us, that a block of a circuit consisting of resistances and independent and dependent sources can be transformed into a voltage source and a resistor here. So how do we determine these values of VTH and RTH? By the way, you can apply Thevenin's equivalent to any part of the circuit, as we've been saying. So let's say we have a circuit given like this. So you could apply Thevenin's equivalent to this part here, right? And if you apply Thevenin's equivalent to this part, this voltage source, and we have 5 resistors, they can all be replaced by a single voltage source and a single resistor. The rest of the circuit, in yellow, it remains the same. Well, if it's of interest to you, you could apply Thevenin's equivalent to this part of the circuit here, the blue part here. The rest of the circuit is here. So now VSS, R1, R2, R3 can be transformed into a voltage source and a resistor. Right? So we are building a Thevenin's equivalent of this part, voltage source. The rest of the circuit remains as same, R4, R5, R6. We are not touching that. We are applying or transforming a part of the circuit into a Thevenin's equivalent, which is VTH and RTH. So that helps in simplifying circuits. And so let's look at how we can determine VTH and RTH here. Okay. All right. So we are saying this part of the circuit is being transformed into a voltage source and an RTH here. So the blue part into a blue part here. The yellow part, the rest of the circuit remains as it is. So the first issue is, what is the value of VTH, the Thevenin's voltage here? So let's separate this circuit from the remaining part here. So let's open this. Let's create an open circuit here, right? So this is opened. So we break these connections here between this part and this part. We break it up. And so there's an open circuit here. And let's say the open circuit voltage is what we call as VOC, voltage open circuit. All right. Now, these two circuits are equivalent. So let's open it up here also. Let's break it up at this particular part. So is broken here. And they are both equivalent. So the voltage here, we know that once you open it up, the voltage here is going to be VTH because there's no current flow. It's an open circuit, no current flow. So it's basically equal to VTH. And the two circuits are equivalent. The two circuits are equivalent. That's what we want them to be. So which implies that VTH equal to VOC. So how do we determine the Thevenin's voltage? What we do is we disconnect the part of the circuit whose Thevenin's equivalent we want to build, disconnect it. So we open circuit these terminals here and we determine this open circuit voltage here. And this open circuit voltage becomes our Thevenin's voltage. So that's our VTH. Okay, as an example, let's say we want to build a Thevenin's equivalent for this part of the circuit here. And the Thevenin's equivalence is VTH2 RTH2. So how do we determine the Thevenin's voltage VTH2? Well, this blue part here, we disconnect. We break it up right here. So we break it up here. And what do? We determine the open circuit voltage here. And what is the open circuit voltage here? Well, this is open. So it's a simple voltage divider. So we can write VTH2. The Thevenin's voltage is nothing but the open circuit voltage equal to VSS. R2 by R1 plus R2. This becomes a voltage divider. R3 is open here. So that's how we end up finding the Thevenin's voltage here. The part that the circuit whose Thevenin's equivalent you want to find and the terminals between which you want to find, you create an open circuit between those two terminals here, right? So you disconnect the other part, you open circuit here, and you find out the open circuit voltage, and that becomes your Thevenin's voltage. How do you find the Thevenin's resistance? Again, what is RTH? So what we do is again we disconnect this particular part, right? So we remove this particular part. We are not interested in this. We are only building Thevenin's equivalent for this part of the circuit. So these are the two terminals across which we are building Thevenin's equivalent. And then what we do is we short these two terminals here, right? We short these two terminals, and let's say the current that flows is in this short circuit is ISC, short circuit current. Well, let's do the same here. We disconnect it here from this part and we short it. And we short it. And when we short it, well, of course, the current that flows in the short circuit is VTH by RTH. Now, the two circuits are equivalent because, you know, this circuit is being replaced by these two combinations here and they're supposed to be equivalent. So then ISC must be equal to VTH by RTH. So ISC must be equal to VTH by RTH. So RTH, Thevenin's resistance, becomes equal to VTH by ISC, and VTH is nothing but VOC. So how do we find the Thevenin's resistance? We've already found VOC in the previous step. VOC was, we found it out in order to find VTH. So we already know VOC. Next is we find ISC. So what you do is the circuit whose Thevenin's equivalent you want to find between the terminals across which Thevenin's equivalent has to be found. First you open circuit it to determine VOC, then you short circuit it to determine ISC, and the ratio of the two is going to be RTH. And that's a simple proof of why RTH is equal to VOC by ISC. So we saw how we can determine the Thevenin's voltage, how we can determine the Thevenin's resistance. And so the summary is that a linear circuit consisting of resistances and independent and dependent sources, you could take that particular circuit and convert it into a voltage source and a resistor between a pair of terminals. Okay, so it's important to remember that between a pair of terminals, the same circuit across a different pair of terminals, there would be a different Thevenin's equivalent here. And how do we find the Thevenin's voltage? Well, you open circuit, create an open circuit across these two terminals, measure or determine the VOC, and Thevenin's voltage is nothing but open circuit voltage. Next, what you do is between these two terminals, you short circuit it, determine the short circuit current, and Thevenin's resistance is open circuit voltage found earlier divided by short circuit current determined in this step, and the ratio gives us the Thevenin's resistance. So this is the procedure for determining the Thevenin's voltage and Thevenin's resistance. So any linear circuit consisting of any number of resistors, any number of independent and dependent sources can be converted into a Thevenin's voltage and a Thevenin's resistance across a pair of terminals here. Okay. Let's look at this same example here. So we had already found the Thevenin's voltage for this particular circuit here. We said that disconnect this particular, you want to find Thevenin's equivalent between these two pair of terminals. So disconnect it here, open circuit it here, find out the open circuit voltage. That gives us the Thevenin's voltage here. Now you want to find the Thevenin's resistance. Well, between the same pair of terminals, you create a short circuit and find out the short circuit current. So the short circuit current, you can find out that R3 is in parallel with R2 and the whole thing is in series with R1. So the current that flows from VSS will be VSS by R1 plus R2 parallel R3. That's the net current that flows here. And this net current that flows here divides between R2 and R3. So we use the current division expression. So the current that flows in R3 will be R2 by R2 plus R3. So once you use these Thevenin's approach, the circuits that you get when you open circuit it or when you short circuit it, the circuits often become simpler, and we can use the concept of voltage and current divisions to determine the answer here. So ISC is VSS by R1 plus R2, this expression here. So our Thevenin's resistance then becomes VOC determined in this step, ISC determined in this step, take the ratio here, and you get the Thevenin's resistance for this part of the circuit here. All right, so we have determined the Thevenin's voltage and we've determined the Thevenin's resistance here. There is sometimes a simpler method for finding Thevenin's resistance in cases where my circuit does not have dependent sources. So the circuit whose Thevenin's equivalent you're trying to find, if it doesn't have any dependent sources, then the process becomes a bit simpler. So again, this circuit, we are saying between these two terminals is represented by VTH and RTH. So the idea is as follows. If we make all independent sources 0, right? If we make all independent sources 0, then VTH will become 0 here. Because VTH, what does it result from? It results from independent sources. If there were no independent sources, there would be no value of voltage in the circuit here. So if we make all independent sources 0, VTH will become 0. Fine. Then, if we make VTH equal to 0 and we look at the circuit between these two terminals, we'll see the equivalent resistance is nothing but RTH. Obviously, if you make VTH equal to 0 between these two terminals, what do we have? Equivalent resistance is RTH. So the idea is that if you want to know what is RTH, you take this circuit whose Thevenin's equivalent you're trying to build, open circuit over this here, and what you do is you make all independent sources, you set them as 0. So now note what happened was we said this is a linear circuit without any dependent sources, right? So if you remove all independent sources and dependent sources it doesn't have, so it's left with a bunch of resistors. So when you look from here, you will get some equivalent resistance. And what will be the value of equivalent resistance? Well, it will be equal to RTH because the two circuits are the same. So when you set independent sources to 0, you will get some equivalent resistance. You set independent sources to 0, you will get equivalent resistance, and the two equivalent resistance must be the same. And therefore, that's how you find equivalent, Thevenin's equivalent resistance in this case. Provided you don't have any dependent sources here, then you can use this simpler approach. As an example, if you want to find out what is the Thevenin's resistance for this particular part, well, so what we do is we take this particular part and we remove all independent sources here. So we short circuit this independent source and we find out what is the resistance looking from here. And this is straightforward. R1 is in parallel with R2 in series with R3. So we write it out and that becomes the Thevenin's resistance, right? So it's a simpler approach. Earlier we had found out this particular expression by short circuiting, by determining the short circuit current and taking the ratio of open circuit voltage and short circuit current, we had obtained this expression. You can easily verify that the two of them are the same here. Okay. Now, complementary to Thevenin's equivalent circuit, we have what we call as Norton's equivalent circuit. So the ideas are very similar, except that in this case, the circuit in which you are interested in, you can represent it in the form of a current source in parallel with a resistor. So this is what we call as the Norton's equivalent, a Norton's current and a Norton resistance. So this part of the circuit and this pair of terminals here you can transform that particular circuit into a current source and a resistor like this here. So in the previous case, we did a voltage source and a resistor in series. In this case, we are saying you can convert it into a current source in parallel with the resistance, and we call that as the Norton's equivalent circuit here. So in this case also, for example, this is the yellow part, let's say here, and you're trying to build the Norton's equivalent between these two terminals here. So the remaining circuit can be represented as IN into RN, IN and RN here, and this is R0 as it exists. So we are saying the rest of the circuit can be transformed into this here, right? So both Thevenin's and Norton's theorems are very general, and any linear circuit with independent or dependent sources can be transformed like this here. So in this case also, our goal of course is how do we find IN and RN here, right? So the way we do IN and RN is, let's start with IN. So we take this particular part of the circuit, we disconnect it from the remaining part. This is the part whose Norton's equivalent we are trying to find. So we take this part and we short it. We short the two terminals here. And let's say the current flowing is ISC. Now note, similarly now, this is the original circuit, this is the Norton's equivalent circuit. So we take this particular part here, we disconnect it from the remaining. We take this part here, we short circuit it here. And the current that flows here would be basically this current here would flow into this short circuit here. And because these two circuits are equivalent, IN must be equal to ISC. So how are we going to find out the Norton's equivalent of any given circuit? Well, we'll take that particular circuit and the terminals between which we want to build the Norton's equivalent. We'll disconnect the remaining part, and between those two terminals we create a short circuit, and we determine the current that flows through the short circuit. And Norton's current IN will be basically equal to ISC here. IN equal to ISC. So this is a simple proof of IN, why IN is equal to ISC here, because the two circuits are equivalent. Norton's resistance, similar approach. We disconnect this particular circuit here, and let's say we open circuit it here. So the voltage here, let's say, is VOC. All right, we take this part of the circuit, we disconnect it, we open circuit here. And when we open circuit here, the voltage at the two here and here should be the same. But we also see that when you open circuit here, this current IN will flow through RN, and so VOC will be equal to IN into RN. And therefore, and we already know that IN is ISC, the Norton's current is obtained by short circuiting the two terminals here. So we already know IN equal to ISC. So from here, we obtain RN equal to VOC by ISC. A similar expression as when we found out Thevenin's equivalent. Right, so the Norton's resistance and the Thevenin's resistance are come out to be basically the same. Open circuit voltage divided by short circuit current here. All right, so these are the approaches for finding the Norton's resistance. Again, similarly, if you have a linear circuit without any dependent sources, then the determination of Norton's resistance becomes straightforward. If you make all independent sources 0, then IN will become equal to 0. The resistance looking from here will be equal to RN. So you take this circuit here, make all the independent sources to be 0, measure the resistor here, and this one also will be equal to, you will get some equivalent value of resistor, but this has to be equal to RN because the two circuits are the same. So that's how, if your circuit doesn't have dependent sources, then the computation of Norton's resistance becomes simply the equivalent resistance between these two nodes after you have removed all independent sources. Okay, so let's build a Norton's equivalent for this particular part of the circuit here. So this is the part here which is being transformed into an IN into RN. So we have to determine IN and we have to determine RN. So to determine IN, what we have to do is disconnect the remaining circuit from this one. We are building IN and across this. So we disconnect it here. We short this here, and we said the short circuit current is going to be nothing but Norton's current here. And the short circuit current is Norton's current here. And how do we determine? Well, we have seen earlier R3 and R2 are in parallel, and the whole thing is in series with R1. So the net current that flows from VSS will be equal to VSS by R1 plus R2 parallel R3. So that's the net current that flows here. And this current divides between R2 and R3. So the current division tells us that the current that goes into R3 will be R2 by R2 plus R3. So that's how we get the Norton's current here. For Norton's resistance, we said take this particular part of the circuit and remove all independent sources, remove it and short it here. All independent sources are set as 0. So when you set VSS equal to 0, it basically means a short here. And then you find out what is the net resistance looking from here. So that's equal to R1 parallel R2 plus R3. So that becomes the Norton's resistance. So this whole circuit of VSS, R1, R2, R3 can be transformed into a Norton's current with a value given here and a Norton's resistance with a value given here. All right, so two very general, very useful approaches for simplifying circuit, and they also help us in understanding the circuit here. So coming back to our maximum power transfer, so if you're given any complicated circuit and there's a load resistor connect to it, and the question that you're asking is what value of load resistor should I attach here so that I get maximum power dissipated in RL? Well, if it's a linear circuit, the problem is simple. In this linear circuit between these two terminals can be replaced by a Thevenin's equivalent. We know how to determine VTH and RTH. And so for maximum power transfer, what do? We choose RL equal to RTH. So Thevenin's equivalent is allowing us to use a very simple result, reuse a very simple result in more complicated cases by building a equivalent circuit in this particular form. Before we leave this particular topic, a very simple case of Thevenin's and Norton's theorem sometimes can be very useful. So let's say in a circuit, you find yourself with a situation where you have Vs and some Rs here. And there may be other elements. We are not showing the rest of the circuit. So there's a Vs and an Rs. So what we can do is, if you're given a Vs and Rs, we can build a Norton's equivalent of this particular part of the circuit. Norton's equivalent would be a current source and a resistor. Now, how do we find this current source? Well, the current source would be if you short these two terminals here. And the current flowing in the short circuit would be Vs by Rs. So Norton's current would be Vs by Rs. What will be the Norton's resistance? It will be the resistance looking between these two terminals here after you've removed the voltage source. So when you remove the voltage source, what is the resistance that you see is Rs. So it's Rs here. So what this is telling us is a voltage source with a resistor connected to it. If you see something like this, you can replace it by a current source with the value Vs by Rs and a resistor in parallel with it. This is what we call a source transformation. A voltage source is being transformed into a current source. And of course, we can do vice versa. If in the circuit you see something like this somewhere, Is and Rs here, well, you could build a Thevenin's equivalent of this. You can always convert it into a voltage source and a resistor. How do you find this voltage source? Well, how do you find the Thevenin's voltage? The open circuit voltage here. So what is the open circuit voltage if I don't connect anything between these two terminals? This current Is flows into Rs. So it's nothing but Is into Rs. What is the Thevenin's resistance? Thevenin's resistance is the resistance between these two after you've removed the independent sources. So removing the independent sources means putting them equal to 0. So when you put Is equal to 0, this becomes open circuit. So looking from here, all you see is Rs here. So a current source in parallel with the resistor Rs can be transformed into a voltage source in series with an Rs here. So this is what we call a source transformation. Anytime you see a voltage source with a resistor, you can convert it into a current source and a resistor if it helps you in analysis. Anytime you see this, you can convert it into a voltage source and a resistor. You can go back and forth here. All right, so let's see a simple example of how we can use it to analyze circuit here. So let's say we have a simple circuit here and we would like to determine V0. And we would like to do it. There are many ways now. You have so many tools in your toolbox. So there are many ways in which you could determine that. You could do it by mesh, nodal, Thevenin's, Norton's, all kinds of things you can do now. So, but what we'll do is we'll use source transformation. So we see a voltage source and a resistor. And keep this diagram in mind. A voltage source and a resistor can be transformed into current source and a resistor with the value Vs by Rs and Rs here. So we'll apply to this particular part here. Okay. So it becomes this R1 and VSS becomes a current source in parallel with R1 here. What is the value of the current source? VSS by R1. So we get this circuit. The two circuits are equivalent. Okay. Now we see R1 and R2 are in parallel, so we can combine them into one single resistor. And the next thing what we do is we take this whole thing is a current source in parallel with a resistor of magnitude R1 parallel R2, and we apply source transformation, this one here. So we can transform it into a voltage source and a resistor. Voltage source and a resistor. What is the value of the voltage source? Well, VSS by R1 is the current multiplied by the net resistance here. So it will be VSS by R1 into R1 parallel R2. What is the value of the resistance here? R1 parallel R2. This is one single resistor. We are treating them as one single resistor with the value R1 parallel R2. Now this whole circuit becomes a simple voltage divider circuit, so we can write down what is V0. So V0 will be this voltage here, and the voltage will divide between these three resistors, so it will be R4 by R4 plus R3 plus R1 parallel R2. So we've obtained a result through basically source transformation. We didn't do any KVL, KCL, we used series parallel resistors, and we used source transformation, and we arrived at a result. And this result is also gives us a structured expression. Once you become familiar with it, you will be able to do many of these steps very quickly, and you can arrive at an answer much faster than, let's say, if you try to do a mesh analysis or other techniques that we have here. All right, so let's summarize. So our toolbox, the toolbox of analytical tools already had nodal, mesh, and then we had analysis using pre-derived results, meaning series, parallel, voltage division, current division. And we also use the superposition principle to decompose complex circuits into simpler. So today we added these three tools: Thevenin's theorem, Norton's theorem, and source transformation. So we have lots of tools in our toolbox which would enable us to take up any circuit and obtain a result quickly, and obtain a result which would give us more insight into the operation of the circuit. All right, so let's stop here.